on vacation. I'm on vacation at a nice resort with my wife. But let's pretend for a second that I have a difficult time relaxing. The only clear solution is for me to plan every aspect of my stay. On the very first night, just the first night, I can swim in one of 4 pools, I can eat at one of 5 restaurants, and then afterwards I can go see one of 3 evening shows. So the first question is, how many different combinations can I make of those elements to make unique evening experiences? Well, let's start by assuming a couple things. One, these steps are only in this order. First swim, then dinner, and then show, and that I can't combine them in any way. So one way I guess I could start solving this is by building a 3-column chart and then list things in the order of most preferable to least preferable. But then I got this problem. How do I know I haven't missed anything? How do I know if I haven't accidentally written down something twice or 3 times? I really can't trust this system if it gets to be too big. Another way to go about this is to make a choice flowchart, where every choice splits off into every other possible choice. And at the end, you've got a whole long list of outcomes that are unique. So if I start with my pool question, I'll take pool number 1, and then restaurant number 1, and then show number 1. Okay, that's one outcome. And as long as I don't repeat 1, 1, 1, I'm fine. Okay, then I'll take pool number 1 again, and restaurant number 1 again, and show number 2. And then pool number 1, restaurant number 1, and show number 3. Now I've got 3 outcomes. Okay, I'm going to stick with pool number 1. I'm going to go to restaurant number 2, and then show number 1. So pool 1, restaurant 2, show 1. Pool 1, restaurant number 2, show 2. Pool 1, restaurant number 2, show 3. Okay, then I'm going to go to, I'm still on pool 1. So pool 1, restaurant number 3, show 1. Pool 1, this is tedious. This is gross. Wait a minute. What did me from the map ask before? How many different combinations can I make of those elements to make unique evening experiences? Oh, that little jerk, Map Me didn't ask for every combination to be described. He just wanted to know how many there were. Well, I guess that simplifies it, but now I'm still doing the same thing over and over again. How many times do I have to do this?
Now I'm going to back up here really quickly for a few seconds just to examine why I was using a web and what my problem was about an itemized list. What I've got here, drawn ever so well in dry erase markers, is a representation of my options. I've got kind of a diving board, kidney-shaped pool, a water slide, some kind of hot tub, and lane swim, so 4 pools. And I've got, I'm going to say fine dining, some sort of bistro, a malt shop, some kind of walk-up food truck, and hibachi style presentation dinner, because I could only draw those 5 things. And I've got, in the world of entertainment, something that I will generously call opera, a rock and roll band, if you squint, and a dancer, if you're looking at this picture just after being in a motorcycle accident with no helmet. So, unfortunately, the best that I've got is on display here. Yeah, I mean, you can count out the number of lines that take you to each possible combination. You can go, okay, 1, 2, right? And then you can go 1, 2, and then and that's the first 3 combinations I did. Then I can start at this pool again and go 1, 2, But you can see just after 2 passes, this is going to get messy. That's what it looks like having just chosen this pool only. And already, I mean, I can't go back and check my work very easily. I can't tell if I've made any really gigantic mistakes. But what I'm noticing here is that if I've counted correctly, I have done 15 trips starting at just this pool so far. And that's kind of good news for me, really, because 15 is the product of 5 multiplied by 3. And so, with this maybe as a proof of concept, I might be able to pursue an easier way. With seemingly equal artistic flair, I've drawn a grid here of 5 squares and 3 squares set in an array. And if you've seen your average times table, you probably know where this is going. So here we've got ourselves 15 squares, and each square represents one part of my evening. So if you want to think of 4 as the food truck row and 3 as the ballet concert, there's only one square that has food truck and ballet, which I am sure is a very classic pairing from all the famous people I've ever talked to. Now, this is just one piece of the ways of combining. There's also that pool question. So if you want to think of this in a different way, you've kind of got to rotate your perspective like this and have a look at the same array from a slightly different perspective. From this slightly tilted angle, we can see that these squares that added up to 15 are actually cubes because they are one stack. And this one is the example of pool number 1 that I had over here before. And with a little bit of stack adding, I can add 15 plus 15 plus 15 plus 15 to have a look at this as it would look if I had a box, a cubey box, for every possible combination of the 3 variables. And when you think about adding over and over again, like I'm adding 15 plus 15 plus 15, well, I'm multiplying again. So in order to find the answer to my first question, I'm really just saying, without having to describe each and every possible combination and all of its artistic merits, it's just 3 times 5 times 4. You can multiply that any which way you want to, but when all is said and done, it will always equal 60 different options. Well, that sounds like some fun. So what was I doing on that first screen with the big web that looked like it was going to explode in this direction? Well, let me show you a quick glimpse at another way to visualize all your choices. Now, when I was hanging out on my hotel balcony, waving my hands around at an invisible net and making the people in the next balcony over believe that I was being swarmed by some sort of exotic mosquito, what I was really gesturing was a web that looked kind of like this. You can see right here is me waiting to make a decision about the 3 things that I was going to do that night. Right here is the part of my evening where I would choose one of 4 paths, whether I'm going to one of these pools and which one I was going to. And each pool splits off into one of 5 restaurants. That's why each pool gets a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on and so forth. And then here in the fine print, you'll see that each restaurant splits off into 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, all the way down the page, meaning that on any version of my night, you'd see a line starting from here and then going to, let's say, pool 3, and then restaurant 3, and then show 3. What I'm left with is 60 tiny ticks. And when you've got a medium number of choices, it's not a bad thing to draw them out in this way. As soon as your choice numbers get larger, then you're going to find that you're going cross-eyed trying to maintain this family tree of insanity. Now, the one additional good thing that we can get out of this is the knowledge that if I had to make another choice, all I'd be doing is multiplying by the next choice. So here's me and one me, and I'm multiplying by 4 pools, I'm multiplying by 5 dinners, and I'm multiplying by 3 shows. I don't know if that's lined up correctly. But then if somebody said, do you want soft pillows or hard pillows? Well, I don't know. I don't know what my brain's worth, but I'd say that's another choice of 2, and then my 60 becomes 120.
Well, finding all the ways might seem on the surface like a silly objective, arbitrary, and conceived by cruel and evil math teachers the world over. But chances are you've either seen a question like this or you're going to one day. And, well, lucky you, because these weird abstract problems are going to help you in the real world of future math classes with their own weird abstract problems, because you're going to have to one day tackle the big umbrella concept of probability.
So probability is a way of expressing something may be happening mathematically. It's a ratio, and oftentimes you can think of it like this. On one hand, you've got the thing or things that I currently care about. And on the other hand, the other side of the ratio colon, you've got every reasonably possible outcome. And you count them out. I suppose that, you would think if you were one of those nitpicky people that if I flip a coin, on one hand it could be heads, on the other hand it could be tails, and on the other hand, a dimensional vortex could open up and a black hole could swallow Michigan. But those things are not equally likely. It's kind of important to think of things in terms of counting off the ways that my wish can come true and counting off the probably equally likely outcomes. Correctly framing reality is kind of important to get a good handle on this. Now, one interesting personal fact about myself is that I'm a big sucker for draws involving boats. If there's some kind of raffle where there's a potential win of a boat, even before I owned any vehicle possibly strong enough to tow it, I would enter that raffle. And to a very, very simple mind, there might be, I don't know, 2 outcomes. Either I can win or I won't win. There's 2 possible outcomes, but that doesn't mean that my odds of winning are actually 1 out of 2. That's a little simplistic. So recognizing, of course, that my art just gets better and better in this video, I want you to imagine the boat raffle in another way. Imagine for a second that I buy 1 ticket. There's my ticket that I bought. And there are a printed batch of 100,000 tickets.
Meaning that my odds are, at worst, 1 out of 100,000 if all of them were sold. We don't know if that's true. It might be that they only sold 10, in which case my odds are 1 out of 10. But the only way that my odds are 1 out of 2 is that they actually only sold 2 tickets. So you can see, clearly determining, accurately determining all the ways can be critical when you're trying to picture the odds of something happening or not happening.
According to the Court of King's Bench and the Hockey Association that kicked me out of a lot of games, I am a licensed trumpet player, and this is a mini trumpet. It is, although you'd think a nasally, squeaky, tiny piccolo thing, it actually plays all of the notes that a normal trumpet would play, and it does so with these 3 valves. Look at that. 3 valves, and it plays all the notes that I play when somebody scores a goal, and then I'm asked to leave by security. It's amazing because the valves can be played in combination with each other. You also can use a little bit of wind pitching through the mouthpiece to squeak up or down the scale, but when I first started playing, I was amazed because look at these. There's 3 valves, and I could play all the notes. So a quick question for you right now is, how many valve combinations are there in total? Like, look at it. Like, you got like that one, that counts as 1, that counts as 1, that counts as a valve combination. All open is a valve combination. So any method you like, can you find an easy way to calculate or find or determine how many valve combinations there are? So never being one to shy away from problems that I give other people, I took on this question myself, and I tried a couple strategies on how to count all the ways the trumpet valves can be depressed. So one way of thinking about it is assigning them each a name. And if you're a trumpet player, you'll recognize these weird little sticks of dynamite with patio tables on them to be valves, and we'll name them 1st, 2nd, and 3rd valves, so like 1, 2, and 3. Depending on which way you're holding the trumpet, it's either this way or this way. But here we go, 1, 2, and 3. Now, one way that I tried to organize my thinking is to imagine how many ways I can play these valves by pushing down no valves. Well, 1, right? There's no valves being pressed down, and there's no other way to play. And then I thought to myself, how many different notes can I play, or how many different combos can I play if I only press down 1 valve at a time? So 1, 2, 3, and that's it. And then the other question I have is, how many ways can I play with just 2 valves? So there's 1, the 1 and 2, and there's 2 and 3 together, and 1 and 3 together. And that's all the combinations I can make with 2 valves. And then I've got the last category, which is playing all 3 valves at the same time. Well, there aren't very many combinations. Either you're doing it or you're not, so 1. Giving me a total of 8. So like any mathematician who refuses to look at the back page, I took on a bunch of challenges to see if I could divine a pattern. And, of course, I could just, Google it, but what's the fun in that? So then I imagined what it would be like if there was a 4th valve and a 5th and a 6th. And I started writing down the combinations, like I just did, of 1 valve, 2 valves, 3 valves, and then if it's 4 valves, 5, 6. And I started getting a weird pattern. Here's what life is like with 3 valves, as I just showed you. And here's what life would be like if I was playing with a 4-valved trumpet or tuba, where I've got only 1 way to play with 0. I've got 4 ways to play with 1 valve at a time. I've got 6 combinations for 2 valves at a time. I've got 4 for 3 valves at a time, and I've got 1 combination for 4 valves at a time. And this is what it would be like if I had a 5-valved instrument, and I kept doing example after example until I realized that I was actually making Pascal's triangle, which, if you want to Google it. It's kind of embarrassing to sort of sit there in the sun on vacation when everyone is splashing in the pool and playing around you and having a great old time, and you're sitting there with your markers and paper working out Pascal's triangle. But I'm willing to accept that I learned something also, which is when I added these up, each row added up to something that you'd probably recognize if you were a musician. 3 valves added up to 8. 4 valves, if you add these up, gets you 16. 5 If you add all these up, you get. And with that in mind, I began to recognize why I was probably working a lot harder than I needed to. Here's the math that really this distills down to. It's actually a lot more straightforward than I thought it was. Every valve has two possible positions. Either it's up or down. Another way that we look at that is ones and zeros. That's why when you see binary, it's like, well, you know, it's only ones and zeros. So it's yeses and nos, check marks and X's. And like I said, every valve has only two positions. 2 times 2 times 2 equals 8. Ah, right. So in the example of a freaky 4-valved tube, now these valves are getting very badly engineered. I've got 2 times 2 times 2 times 2, which equals 16. 16 possible combinations. And this all of a sudden starts to look a heck of a lot more like our very first question of how do I spend my evening? You're about to blow, and your first valve could be up or down. And if the fourth valve is down or up, whatever, you've got another pair of choices to make. And next thing you know it, you got yourself 16 possible outcomes. And you are ready to play things at people. That said, when you look at this question, 2 times 2 times 2, there's another way that you're going to probably see this get written somewhere. And it's this. Two to the power of 3. Really, writing it as a power is probably just there to save space. There are going to be many questions where the number of options for each thing is equal. I mean, if I was dealing with, in the very first question, 4 pools and 4 restaurants and 4 shows, it would be 4 times 4 times 4, also understandable as 4 to the power of 3. 4 times 4 times 4. You could write it that way. So in the question with the trumpet valves, each valve only has 2 choices, and there's 3 of them. You're going to see exponents. So if I want to describe that 2 to the power of 3 or 4 in a more general way, I might describe it with these words. I realize that the expression options to the power of instances sounds like a motivational series of videos. If you're interested in getting in the world of investment banking or something, but it really does describe exactly what happened. The number of options on each valve is 2, right, up and down, given the problem. And the number of instances, the number of valves, because they're all the same, they have the same number of options apiece. The number of instances in that case was 3 or 4. So it's 2 times 2 times 2, or 2 times 2 times 2 times 2. So let's try this thinking out with a different question and see if you can find all the ways this next little mini story can go down.
Magic story time!
So in this story, Mikey has the opportunity to go out on 3 different occasions, and he wants to pick a striking hat to wear on each occasion. He could wear the same one 3 times in a row. He could wear all different hats. He can only wear one hat at a time.
7 hats in all.
So the question I have for you is to describe all of Mikey's Monday, Wednesday, Friday night hat combinations. How do you best describe it? Is this hat thing described best as 3 to the power of 7, 7 to the power of 3, or what the heck? It doesn't matter because you think they're both the same. Well, in this case, Mikey has 7 options. They don't change every night. Of the 3 nights, there are 7 options. Options are 7. And the instances that he can dress up and look fine, there are 3 of them. So 7 to the power of 3, aka 7 times 7 times 7.
So after my exciting first evening of swimming and eating and watching stuff, I have a new problem. And it's that I have forgotten my room number. I got one of those electronic cards, but it doesn't actually have the room number on it. And all I remember is that it's a brown rectangle, probably brown, maybe wood. Beyond that, I'm not sure. So now I want to calculate the probability of finding my room in a truly random guess. So here's a look down the hallway of the resort that I'm staying at. And you'll notice that every door has a number, and every number has 4 digits. So the question you can ask yourself is, how many possible addresses can you make with a 4-digit number? Whether you said 9,999 or 10,000, one way to conceive of it is 10 times 10 times 10 times 10. 110 for each place value in base 10. Fortunately for me, there's nowhere near 10,000 rooms in this resort. Well, like I said, there are 4 numbers to every door. But each place value means something different. Door 2317 means that it's building 2, and we're on the 3rd floor. And in the 3rd floor of the 2nd building, I'm on room 17.
So looking at this facility as a whole, let's try our best to figure out how many rooms it actually has. So this facility has 1, 2, 3, 4, 5, 6, 7 hotel buildings, large structures that have rooms in them. Each one of those has 4 floors apiece. And based on the way they all lock together and zigzag together, as far as I can tell, each floor has 37 rooms. So instead of 10 times 10 times 10 times 10, what we're really dealing with is 7 times 4 times 37. And that's the number of rooms we get, which multiplies out to 1,036. So the odds of me guessing in one try which room is mine in a blind draw is 1 out of 1,036. It's not great odds, so I better call the concierge as soon as possible.
But when it comes to probability, finding all the ways that something could be done is only part of the issue. Being clear about the number of things that I care about, that little number on the other side of the ratio, is also important. Take dice, for example. Look, we can all agree that when teachers start bringing gambling directly into the classroom, it's a weird vibe. But whether you're playing Monopoly or backgammon or craps, a good roll of a fair pair of D6 dice, a fair roll, not one of those nonsense pick up and set down gently things that your cousin keeps trying to pull when you're playing Monopoly, an actual roll. Nice try, Jeremy. Sometimes is the difference between success or failure.
While dice normally come as a match set, I actually found a second die that was green so that you could tell them apart. It's important to think of them as individuals, and they just happen to be getting rolled at the same time. Each die has a 1 chance out of 6 of landing on any specific number. But in combination, we kind of have to multiply everything that this one can do with everything that this one can do. So out of 36 total possibilities, what are the odds of rolling some of the following? So the first question is, what's the probability of me rolling 2 dice and getting a 12? Well, basically there's 36 outcomes, which we kind of figured out from previous questions, 6 times 6, and there's only one way to make a 12, and it's right there. Now this strategy of how many ways can I do this becomes important when you ask the next question. How many possible ways can I make 7? What's the probability of rolling 7? What out of 36? Well, I mean, if you look at the dice, and that's why I have them different colored, you'll notice that the 3 white 3 green 4 and the green 3 white 4 are different combinations. So every combination is marked here, and there are 6 of them, so 6 out of 36. If you know anything about ratios, you can reduce that to 1 out of 6 because you can divide both the left and the right by 6. But for the purposes of comparison, I'm going to keep them all out of 36 so that they're easier to see. Let's do another one. What's the odds of rolling doubles? Well, I mean, 1 and 1, 2 and 2. As you count them out, you realize, yep, exactly the same odds as rolling a 7. There's 6 ways to do it out of 36 potential outcomes. All right, so let's get even pickier. What's the probability of them both being odd? Okay, so a 1 and a 3 or a, yeah, I mean, if you kind of do one row, you realize there's a pattern. And sure enough, they're both odd. Now you can actually say that it's 9 out of 36. You can divide both the left and right number by 9 and get 1 out of 4. But if you zoom your focus into just one of these boxes, you'll notice that you've got yourself 1 yes out of 3 no's, and that pattern actually replicates really nicely throughout the entire grid, so it's kind of not surprising that you get 1 out of 4 odds of rolling a double odd roll. So what's the probability of rolling 1? Well, it's 0. It's 0 out of 36. It's 0 out of everything, frankly, because there's no way to do it. You can't roll a 1 because the smallest number you can roll with 2 die is 2. All right, let's get a little pickier, but it shouldn't scare us off. What if it's the probability of rolling 1 6, either green or white, and an odd number? So to plot them on this chart, there's 3 there in the green 6 column, and there'll be 3 more in the green 6 row. So 3 plus 3 is 6. Seems that 6 seems to show up quite a bit in these questions. It's not my intention. Hopefully we'll find some more examples that are not 6. So as a little exercise, using what we've just done, here's a weird question. Somebody wants to know which is more likely, a pair of unequal prime numbers or any pair of composite numbers. All right, so to remind you, prime numbers are numbers that you can only divide by themselves and 1. 2 is a prime number, 3 is a prime number, 5 is a prime number. 1 should be a prime number, but often gets pulled from the list. I don't know. It's a thing that people can argue about and yell at me about later, but right now we're not including 1. It's just 2, 3, and 5, but they can't be equal. It can't do double 3s. Okay? And then with the dice, any pair of composite numbers. So on the other side, 4 and 6 are composite numbers because you can divide them by things to make them smaller other than by themselves. Okay, so which is more likely? I know you're just excited to find out. Well, taking the first one, unequal prime numbers, we mark them down and take away the ones that are like a 2, 2. Right? 2, 2 can't be there because then it'd be equal. That wouldn't work. Or 5, 5. So it leaves us with 1, 2, 3, 4, 5, 6 again. 6. Accidentally, trust me. All right, compare that. Here would be 6 out of 36. That's your odds. I'm not going to reduce because this one's probably going to be out of 36 too, and it would be nice just to compare that 6 to whatever goes right here in a second. All right, any pair of composite numbers. Sure, 4 and 4 can be a pair. 6 and 4, 6 and 4, 6 and 6, but that's it, just 4 pairs. So what we could say is that the odds are higher to do this thing than this thing. There's more ways to get this done than there is to get this done. Therefore, the probability is more likely that this will happen instead of this will happen. And that's really how probability works. If I say, are the odds greater in rolling a 12 or rolling anything except a 12? Well, there's one way out of 36 to make a 12, and there's 35 other potential rolls that are equally likely to take place. That could be the not side. So whatever number is bigger is more likely. So for some questions that we've taken on so far, we've either used the outcomes to the power of instances. The other version of this is a little bit more picky, like the very first question I asked, possibilities multiplied by possibilities multiplied by possibilities. But there is another question in the family of find all the ways, and it's when things are not in order, when things are not lined up, and they could be shuffled around. And that's a really important question. How many ways can things be reorganized?
So if you're dealing with a situation where the pieces could be put in any order, the previous strategy of multiplying by multiplying by multiplying won't necessarily work. Take these chess pieces, for example. How many different orders can I make with just one chess piece? One, right? How many orders can I make if I have two chess pieces? Well, starting from this side, I've got tall, short, and then short, tall. So 2 orders. Okay, how about 3 chess pieces? I've got them organized shortest to tallest. That's 1 order. And then I've got 2, 3, 4. Well, there's a whole bunch. What about 4 chess pieces? What am I doing each time? How many more am I adding each time?
So to answer this question, let me introduce you to the new math operation, kind of. It's a factorial. It's actually got an exclamation mark inside. It's not that I'm enthusiastic to share this with you, but that's the symbol that we use when we describe something being a factorial. Some of you might know what a factorial is, and I'm very proud of you, but most of us don't. And it's a very specialized, specific thing that you don't see very often. So I'm going to show you what a factorial is in the frustrating tradition of showing you a bunch of examples and then making you figure it out. Let's see what the examples are. So the first statement is 1 factorial equals 1. Well, that admittedly does not give you a lot of information. A factorial could be any number of things. This isn't helpful. Sorry, moving on. Okay, all right, this also is not very helpful because 2 factorial equals 2 still doesn't give you very much to go on to intuit this. I'm going to keep moving ahead. Okay, 3 factorial is 6. That's interesting. It's not what the previous letdowns have been. The numbers are getting bigger. 4 factorial is 24. Okay, well, I'm looking at this 6 and this 24, and I'm kind of wanting to know if something's going on here that's unspoken, perhaps devious or inappropriate. Moving on. 5 factorial is 120. All right, well, I'm noticing that right off the hop, I can divide 120 by 5, I can divide 24 by 4, I can divide 6 by 3, and I guess if I was desperate, I could divide 2 by 2 and 1 by 1. Oh, I think I see what's going on here. Just in case, have a thought about the order that I've shown you these and see if you can guess what 6 factorial might be. Good bet it'll be bigger because each number's gotten bigger so far. But it's the sequence that becomes important. I'm not going to sit around all day and make you guess. I'm actually going to show you, so don't hate me. Or hate me, I don't care. So looking at 1 factorial equals 1, well, still, I can't show you much more than that. There's no help there. But if I show you 2 factorial, 1 times 2 equals 2. All right, I don't know if you saw what I did there, but I'll show you again on 3 factorial equals 6. 3 factorial can also be written as 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. And 5 factorial Is 1 times 2 times 3 times 4 times 5. Yes, it really is that simple. We're just multiplying a list of numbers starting at 1 and going as high as the number says next to the exclamation point. So 6 factorial, as I'm sure you can probably guess, is 1 times 2 times 3 times 4 times 5 times 6, which equals 720. The one thing that you gain out of this is if you ever had to find out what 33 factorial is, you wouldn't actually have to sit there on your calculator like a dope typing 1 times 2 times 3 times 4 all the way up to 33. You could probably just either find a function on a calculator or, Google it, what is 33 factorial, and it'll just spit out the answer. It's big, by the way, and we'll get into some big numbers later.
And this is the key to figuring out any question where you've got a scrambled list. When you've got 4 chess pieces, it's 1 times 2 times 3 times 4, 24 different lists of those same pieces. 9 baseball players can be arranged into 9 factorial batting orders. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 gets you 362,880 different orders. It just does.
This is where the wording of a probability question is so critical. So if you're being asked to do a blind draw out of a random deck of cards, and you're asked to pull out the ace of spades, for example, then your odds of doing so are pretty easy to calculate. There's 52 cards in the deck, and there's only one ace of spades, so your odds are 1 out of 52. Now, if your goal is to draw out the ace of, diamonds, blind, okay, and then draw out the ace of clubs, and then the ace of hearts, and then the ace of spades, then your odds are much more gargantuan against you. 1. Let's see if I can get the next one. 2. They're in here somewhere. 3. 4. Well, what your odds are 1 out of 52, and if you get that right, then you multiply it by 1 out of 51, the rest of the cards in the deck, then 1 out of 50, and then 1 out of 49. Of course, unless you cheat. It works out to a gigantic number. Now, if your goal is to shuffle the deck completely and randomly and totally, and then by sheer chance have it rearrange all the cards that you predict are in, there should be one of each, and rearrange it into a specific order. Say, for example, the very first order that it came in when you bought it, then your chances of doing so are even worse. There's our 4 aces. I'll mix them up a little bit. But if you want to really, really, pick one configuration out of all possible configurations, then your odds are 1 out of 52 factorial, that exclamation one. And it's something like 1 to 8.0. I'll put it on the screen. It's humongous that you can actually do it. So let's see how lucky I get with this random shuffle. Well, nobody's perfect. Okay, this is the last question. It is a question that asks about all the ways and requires you to be meticulous in the way that you count all the ways. And it asks you about the probability of certain things happening or not happening.
And after this, you can go do the worksheet I gave you, or not, or I don't know, go to lunch or not. It's kind of up to you and your teacher. You guys figure it out. So in this story, you are helping somebody. An engineer is designing a carnival game. It's a game of chance, like a penny arcade thing, in which tourists drop a single coin. And there's the single coin. So the coin randomly falls any which way, bouncing off a series of posts, bing, bong, 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 that give it a fair chance to fall to the right or left. And I think the important thing here is that any gate that it hits, it can either move left or right, meaning that if this thing fell here, it can't jump all the way over there. If it falls here, it can only go there or there. Can't go up, it can't, teleport. It really just has a series of left or right, left or right, left or right. All of these are left or right. So the coin eventually lands in one of 6 baskets at the bottom. And a player might win a prize depending on which basket their coin lands in. As you can see, there's some payout symbols here. So in this game, if your coin that you drop in lands here or lands here, then you win 8 coins, you, the player. If the coin falls down and lands here or here, the way the game is currently designed, your player, the player, will win 4 coins. And if it lands here or in here, they win nothing. And they have to just kind of swallow that disappointment. So your task, as I'm reading to you, that you can see, is to tell the game creator if you think that this game will be profitable for its owner. Because if the machine pays out too much money, carnival owners won't want to buy it. So the challenge here is to try to figure out all the ways something can happen. And it's pretty clear, I think, on first glance, that the outer jackpot pots are positioned pretty well. This coin has to fall exactly and only one way to get here. There's no way for this coin to go this way and then try to work its way back over to the left jackpot. It'll never get there entirely and blunk lose. And same with this one. On this side, the penny, the peso, will bounce around, and only if it makes the exact correct series of choices that a penny is known to make, will it land here and, big win. Meanwhile, I think it's pretty clear that there are probably a bunch of different ways for you to get to, let's say, this zone here. So if I went down, no, that's actually not as easy as I thought it would be. Let me try another way. Plunk, 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 plunk. Okay, so that's a way to get down here. Another route might be all the way down this edge, and then just at the last second, kaplunk, drops in here. I'm curious, though, if there is an easy way to count up all the different ways that a penny can fall, a peso, can fall from the top and land in each one of these baskets. We kind of are getting the sense that these ones are hard to get to, but the ones in the middle are going to determine whether you make a lot of money or not make a lot of money. Is it easier to fall into these baskets or these baskets? And is there an easy way to compare that out to each other? Well, yeah, there is. I'm just going to show you a little peek because I did some trials earlier, and it looks like this. The peso can fall down one chute, and I'm just going to cover up the rest of the game just for a quick second. And there is one path to get it to fall to here, and there's one path to get it to fall to here. See, whenever I have a really complicated problem, I try to invent an easier version of the same problem to kind of think about, and then I can begin to work my way up to the complexities down here. So I'm going to do this very simple version. I drop a coin in here, one root in, and there's one way to go this way and one way to go to this way. So if my game actually stopped at this level, it would look like there's 1, 2 outcomes, and it looks like my coin can go into either one of them equally likely. So it seems to me that this version of the game actually is kind of a 50-50 situation. All right, so with this version of the game, I've made it a little bit bigger. The coin can go down here, and there's one route to get it to this spot. It can go down here, and there's one route to get it to this spot. And then to get to the middle, I've got up a plunk, 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 and up a plunk, plunk, plunk that gets it here. So there's 2 ways for it to wind up here. 1 plus 2 plus 1 is 4, meaning there's 4 possible outcomes, 4 routes this penny can take. And it looks like the middle option is twice as likely as either option. So 50% of the time, 2 out of 4, the coin will land kaplunk right there. All right, so let's make the question a little bit bigger. Okay, I guess it's not too surprising. Doing all the routes that I did, I sat there with my geometry kit and I sat there with my markers and worked and worked and worked. And here I find that, yeah, so not surprisingly, there's one route to get to here, and we kind of already knew the outer edges were going to be harder to get to. And then this one has 3. So plunk, 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 and then a sharp turn inwards plunk, 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 a sharp turn inwards plunk, and let me see here, plunk to here, plunk to here, plunk to here. That gets you that 3. And because it's symmetrical, it's not too hard to imagine why this would be 3. Okay, all right, so right now, if the odds were being analyzed on a game this size, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 outcomes. And here I am, 1 out of 8 in this bin, 1 out of 8 in this bin, and 3 out of 8 in this bin, and 3 out of 8 in this bin. Okay, so more complicated, and it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Yeah, you can count them out. There's 6 ways to get through here. Taking the wide track out, and then the wide track out and in at the last minute, and this, and then bouncing off of those. Huh. Wait a minute. 1, 5, 10, 10, 5, 1. Yeah, wait a minute. So you're saying that there's 1 way to get to this bin, there's 5 ways to get to this bin, there's 10 ways to get to this bin, 10 ways to get to that bin, 5 ways to get to that bin, 1 way to get to that bin. What is happening here? 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 2. Wait a minute. Yeah, I guess. No, yeah. Oh. Yeah, I did it again. Typical. You know what? You guys solved this one. How would you rearrange these jackpots? Would you move these coin jackpots here or out or there? I don't know. But you tell the machine guy what to do. I'm done. Stupid Pascal's triangle snuck up on me. I'm done. I'm done.
Just got lightning crack in the background.